This is the first of several panels we'll be having over the next 3 days. My name's Keith Clarke. I'm the Professor of Geography at University of California, Santa Barbara, and chair the IUCRC Spatiotemporal Innovation Center at Santa Barbara. I'm not going to speak for very long. I'm going to introduce our 4 panelists so they can introduce themselves. The format I'd like to adopt is for each speaker to make a brief opening statement, perhaps kept to no more than 5 minutes, and then we'd like to use the remainder of the time to have, or to begin the discussion around today's symposium. So our first panelist here is Huadong from the Institute of Remote Sensing and Digital Earth. Would you like to say a few words, just to introduce yourself? You can come to the podium if you prefer.
Here, that's okay. So say again, my name is Huadong Guo. From China, Guo means my, the last name. Huadong is my first name. So don't forget that. Quite often people say, Mr. Huadong. No, it's wrong. Mr. Guo is correct. So my name is Huadong Guo from the Institute of Remote Sensing and Digital Earth. The institute belongs to Chinese Chemical Sciences. Because the Chinese Chemical Sciences now, we have the 105 institutions. So among them, several institutes related to the remote sensing technology. Several, related to the remote sensing applications. But the total we have about 15 institutions, the work related to the Earth vision technology, fundamental research, and applications. So recent years in this community, we really, our community is the people really interested about the big data, because in the commercial world, network on the world, a lot of even in the the government agency, a lot of people really use the big data to do a lot of the works. But in the field of research, especially some fundamental research, especially for earth science, the field, not too many people do use the big Earth data to do something. So I really want to mention again. So big Earth, what's big Earth data? Not because just the big, just so many much data, big data. So most important one, big data can promote your research methodology. Maybe give some innovation methodology. But the second one, just read the big data, we can get some scientific discovery. I do think it's the most important 2 issues. So our team, recent years, just or in the next several years, we keep this direction to do that. That's why in my slide just now I mentioned one project entitled Big Earth Data. So the Big Earth data, we should work together. How many people? 1,200 people. Among them, about 241 professor and associate professor level that came from the 29 institutions, of Chinese Chemical Science, and also outside the kids should work together. So this excellent workshop, I do hope we can do some collaboration, bilateral or multilateral collaboration with all of you. Thank you so much.
Thank you, and it introduces the issue of big data and whether it's a facilitator or an impediment to doing research in spatiotemporal computing, something we can discuss. Second, I'd like to introduce Robert Stewart. He's with the Oak Ridge National Laboratory in Tennessee, and perhaps you'd say a few words.
Is this the 5-minute part?
This is the 5-minute part. All right. Would you like me to sit down? Go over here.
So I am Robert Stewart. I am from the Oak Ridge National Laboratory, and I can't really talk anymore without PowerPoints. It's a process of going up in management. So Keith said I had 5 minutes, so it shouldn't take more than 7 or 8 to get through these. But I thought before I talk too much to tell, I'll sort of come from a very wide perspective to a very narrow perspective. And I thought I'd start with the Department of Energy National Lab. Sometimes when I come to these talks, not everyone really understands what a DOE National Lab is, or that they even exist. So Oak Ridge National Lab is one of a constellation of national labs that the Department of Energy has under its auspices. These labs are scattered across the country, and they range, do an extraordinary range of research and interesting innovation in a range of fields primarily centered and related to energy and all things that depend upon energy. So we also do transportation, we're interested in land use, we're interested in also national security and defense as part of our portfolio, and we do a lot of research for other agencies as well. So that's what they look like spatially. Oak Ridge National Lab is the constellation's largest national laboratory. There's about 5,000 or so people in Oak Ridge working on everything from astrophysics to demography. I sometimes describe it as kind of like a university with military protection. We have almost every department that you can imagine at a major university other than, let's say, the liberal arts colleges. We have them there. Now, in terms of conceptually where they lie, we have on the far left sort of where academia sits, doing basic science. On the far end is serial production, sort of industry. And so the national labs are really situated right in the middle of those two. We sometimes look like academia. We have summer students. We have we serve on committees. Some of us teach classes, but we look a little like industry sometimes in that we produce these long-term, long horizon, large commitment type solutions that are in space. So if we dive down a little bit to where I sit, sort of a very simple hierarchy up there. We have Oak Ridge National Lab, and then I sit in that division, and true to the trend, the smaller the department, the bigger the name. So I'm in Geographic Information Science and Technology group. It's about 100 or so research scientists in that group, and you can see the pedigree varies widely. One of the things that's very interesting about GIST is that we're the only Geographic Information Science research group that's situated as a major component in the National Lab infrastructure. And we happen to be housed right in the Computational Sciences and Engineering Division, where we have access to a whole range of high-performance computing environments, including the Titan computer, which is about to be, its credentials are on the left, around 20-plus petaflop peak, and it's about to be replaced by Summit in about a year, which we expect about 10 times that computational performance improvement. So it's a really unique opportunity to do geography and geographic-like science with these kind of assets around us. Very quickly, and maybe this is too much, but I thought I would talk a little bit about the work that we do in terms of big data. And I'll start with imagery and remote sensing. It's everything from the nuts and bolts of photogrammetry, stuff is location correction, all the way down to various types of knowledge discovery. And in betwixt the two, we have a whole range of folks looking at machine learning algorithms to exploit imagery for various reasons. Here we have one of our signature projects. We're charged to map every building in the world. It's a huge undertaking. We're doing that with convolutional neural nets. And then over there, we can combine that with ground knowledge, I call it, to sort of begin understanding socioeconomic conditions that can be detected from those images. And then I always like this slide because we all talk about big data and volume and veracity and all this stuff, but there's a lot of data out there that I call big enough data. It's too big for you to process on your own using Excel, and it's not imagery data. So we have to do a lot of work in high-resolution demography, reconstituting, sort of reverse engineering census data. From that, where are people at in the daytime is a key aspect for us. It impacts a number of things, including energy and security. All the way, of course, we're involved in social media for a whole range of things, including understanding population dynamics, to understanding power outages along the coast, or wherever it is. Here it's along the coast from a hurricane. And then we develop a whole suite of tools. So we have that mandate to try to go one step further in the publication, produce some tools that allow analysts to engage these types of data sets and do at least some exploratory data analysis to sort of uncover hidden trends and patterns in the world in very high dimensional space. And then finally, we have these modeling and simulation tendencies to us. We would leverage all this data, link it together to produce things like the Landscan products, which is a population distribution model that for the US, it's 90-meter resolution of where people are at most likely during the daytime and during the nighttime. It's important for a variety of reasons. We take our demography results and leverage that against energy consumption knowledge and surveys that we've picked up to do really high resolution neighborhood level energy modeling consumption. On the other side, outside of the US, here's a good example where we do a Syrian refugee escape routes, we'll call it, for folks that are not interested in walking along the roads. There's a fear there. Where might they go? It's a combination of cultural and physiological knowledge we have about human transport walking. They have to do it on foot. And then I wasn't really sure when I read what beyond meant. We're still working in the now a little bit. But I guess if I had to say our beyond, we're thinking about it's in terms of just continuing a long arc we have for deep uncertainty modeling and propagation. We want a deeper integration of satellite and ground. So if you have satellite imagery here and you have Flickr, Google Street View here, what can we draw from that? What can we learn from that space? And also ground means census, social media and the rest. Full motion video we're keen on, and we're starting as in the last week or two, conversations about the role of quantum computing in GIS. So that's my spiel. Thank you.
Thank you. It's nice to see quantum computing finally making it into the agenda. It's something that's going to be very transformative. Our next speaker was Dongmei Chen from Queen's University in Canada, and she's going to speak, I believe, from where she is.
It's working. First, I want to thank Professor Yan to put me in the panel actually in the last minute. So I need to apologize. I didn't prepare any of the slides. But I think today here, I think I want to share some of my point of views on something about big geospatial data. I think before I go to talk about issue, I want to just probably introduce myself a little bit. When I first see my name in the panelist, I thought, why? Probably it's because I'm from Canada. Actually, I'm from Queen's University, the Department of Geography and Planning. And actually, the place is not too far from here. It's actually in the border of the US and Canada. In the last, I think I would say about a decade, I have been working with different, I think, government agencies and industry on geospatial the data and trying to using those data in health and environment applications. So I think I sort of have survey, I would say, contradictive issues come out from what we call the big geospatial data. The first things I think I want to talk about is about the data quality and the responsibility of the data and how we should use the big geospatial data. The motivation, actually, I want to talk about this, actually, is from my experience a couple of days ago. I was driving to a cottage around a very remote area in the lake in Canada. And then I was using the GPS, right? And then the GPS basically followed and then said, oh, keep driving. And then I saw a body of the water in there. I said, why in front of there? There's the lake. How I can drive in there? There is, there certainly, I can see there is, that's wrong. Okay, that's the wrong direction. If I follow the direction from the GPS, I'm going down to the lake. Okay? So I don't know how many of you have experience, okay, to the GPS led you to the wrong route. Okay, so that make me thinking about, okay, wow, how accurate our geospatial data and how we could trust those data. And also I see a trend of, I think now, especially in Canada, I'm not sure the situation in other countries. In Canada, I think most of government, since I've been working on the different government organization, and the one trend is the government actually now trying to take off the load of the responsibility in terms of the data, distribution of data. And if you go to the government and ask them for some of the data, they were more likely to say, oh, okay, well, go to these organizations, right? Or this company, and then get the data from there. Or go to the online, okay, they have open, whatever, the government promoted the open data initiative, right? They have lots of data online. And so now we have, and I think the government certainly basically asked them, why, the data, you have the data, why you just give to me? They feel like, well, if you use my data and then let's say something's wrong, and if you sue me, sue the government, right? And then, well, we can't take that responsibility. And so they basically give the data to either to the open access or go to the private company to use the data. But the private company, they basically use the same data, right? And they're sold to the public or sold to the researchers. What I see is, if something wrong, who I should ask, who I should go back to, to looking for looking for some of the metadata in terms how the data being connected, and what's the accuracy on that. Right now, I think there is. I don't think we have any of regulation or rule or some of the law on this. And if you look at it, if you go to the different conference and then go to the medium, you seems like, wow, we're really entering into the data rich. The big data, you have so many, people have been posting a lot of data online, and then what's the quality? How we should use them? You often, like the professor, often what I heard is the student come to me, Professor Chen, how I can find the right data for my research. It looks like we have, we should have whatever the data, a lot of data, but when actually you go to do the research, you will find actually it's not that easy to get the right data. So as the community or as the data provider, do we have any of the rules? What do we have any of the standards or infrastructure should be built up to direct the people to get the data which are appropriate for the applications? So that's, I would say, that's kind of the question or issues which I have been seeing. I think as the academic community, we probably need to think about this kind of, this kind of issues when we go far. Data processing or scientific or technology aspect of, big geospatial data. Thank you.
Thank you, Chen. Certainly these ideas of accuracy and uncertainty have been with us for many years in GI science, but I see they take on a new dimension when we enter the big data era. So again, with our brief introductions, let's try and keep them brief so we have some time for discussion. Lastly, I introduced Wenwu Tang, University of North Carolina at Charlotte. You have hopefully less than 5 minutes.
Thanks, Kate. Also, thanks, Professor Yang, for this great opportunity. So I don't have PowerPoints, so but I want to briefly introduce myself and also the work that I has been doing in terms of spatial temporal computing and also related to the big spatial data. So my name is Wenwu Tang. I'm the associate professor at the University of North Carolina, Charlotte. I'm also the executive director of Center for Applied GI Science. So our center has a focus on the use of these space-time theories, methods, and also technologies to tackle those spatially related problems. So for the over the past few years, we have been working on using the those advanced cyber infrastructure as advocated by Professor Yang, and including the high performance and cloud computing to accelerate and also enhance the spatial temporal problem solving. So I have been working on developing those methods and technologies to tackle those problems within the spatial temporal context. For example, use of we developed the GPU accelerated algorithm to enable the processing of large scale of those massive LiDAR datasets for the entire state of North Carolina. So for the at the method of for the sequential computing could be at the monthly, the several months of computing, we reduce to hourly level. So that we have those GPU clusters, and also we have those Windows clusters, about hundreds of CPUs that allow us to parallelize and also enhance the problem solving. For example, the data quality. So we have been using those data quality. those big Earth data a lot. For example, the NASA's DM, those SRTM data and different data sets to accelerate the processing, the resolution of those complex spatial problems. For example, we have been working with NASA, USDA, Forest Service for the study of global mangrove, so that we combine the DM data with the land use and land cover data, try to extract the canopy height, the biomass and carbon information of those mangroves. So we have developed and deployed those algorithms, parallel algorithms on our Windows cluster, because fundamental algorithm we just leverage on those commercial GIS software and open source GIS software like ArcGIS, Quantum GIS. But if we use scientific workflows to assemble them together, we have to have those computing toys to accelerate that. So our choice is to use cyber infrastructure, use high performance computing and cloud computing. So I was originally trained as an agent-based modeler, so which is a spatial temporal simulation approach. So I have been developing those simulation approaches accelerated by those high performance computing technologies. For example, we have successfully developed those spatial simulation algorithm, for example, based on Professor Clarke's Through model to study the urban growth in the Southeast U.S. So, and all of these are based on the high performance and computing technologies. So I'm a fan of HPC, cloud computing, cyber infrastructure, and also I'm more interested in using those computing technologies to tackle those spatial, complex spatial temporal problems using the big spatial data. Thanks.
Thank you. So with a reminder that our session title is Big Spatial Data and Beyond, we'll now open this up for questions. I just request that if you have a question, please wait for me to get you with this microphone and this so that we have a complete video record of the session. So with that, let me say, any questions? Of course, it's right at the back.
So I've heard a lot about how the spatial aspects and how the data is being stored spatially, but I'm really interested in how you're combining it with the temporal data that's obviously in the data that's there, and how are you doing finding information or knowledge from the both spatial and temporal together. Could anybody comment on that without, that's where my interest is.
I can try.
Okay, please do.
So that's, oh, sorry, I turned myself off. So that's kind of the whole, in my mind, that's kind of the point of the conference, is exactly your question. How do we do spatial temporal computing? Sometimes it breaks apart, some of the conversations do, into either temporal or spatial. So I can speak a little bit about that for one of the projects that we're doing, where we are interested in studying national and subnational behaviors across many, many, many attributes. The thing about nations and subnational entities, as we call them, is that they change over time. They evolve, they split apart. So not only do we are interested in the things that they're doing, but we're interested in their evolution themselves. So to answer a partial answer, I think, to your question, is we use a database that is sort of ontologically rich that allows us to, first of all, get a good foundation on our spatial elements. Then each of those spatial elements have behaviors, we call them attributes. So at the national level, you can imagine it's birth rate, GDP, subnational violence, so on and so forth. And what we're interested in doing is, in one case, we'll do a sort of a time series type clustering of behaviors. But then when you see those clustered behaviors sort of given a score or a semantic label, then we can see them displayed on a map. And at that point, we are able to do sort of spatial analytics on those temporal behaviors. So imagine if you had a map that showed a map of erratic behaviors, where erraticness was came from an analytic that was based on entropy, for example. There's a talk we're doing later on that. Then you could see a spatial temporal map in a single static image. I don't know if that was a good answer or not.
Yes, please.
Well, one resolution is about the data cube. So around the world now, different organizations do the data cube. I really think it's a good idea to give the resolution about the question what you mentioned. Right now, for the data cube, I think the EU data is the first priority, because we do analysis like some environmental study, so we should use the dynamic, the data. So we need the temporal data. Another one, just spatial data. Spatial data is really not easy to do that, but use kind of or beginning to study of like some kind of the Earth version data, like remote sensing data, and like the US the TM, and like what I mentioned, the France support. So because already give some very nice geometrical correction, it's easy to do some spatial computing. So I do think the data cube is one resolution. Thank you.
Just, I can't resist adding my own part. And this is, we do have a couple of models in which we use already for computing. One is the snapshot model, in which we have very much the data cube, the remote sensing approach, where we have time 1, time 2, time 3. And the issues around there are how do we conflate those together spatially and temporally, because even a misregistration in space appears as a dislocation in time, which is problematic. Then we have the event-driven models of change, in which we have periods of time, durations where not much is happening, and then sudden changes. And I always use geological time as an example, where on a Tuesday we go from the Cretaceous to the Jurassic or whatever, but there's not much changing with it within the interim period. Event-based models are driven by single events in time, like an earthquake, for example, with its own successions. Much of the rest of the computing has been around process, how do spatio-temporal processes operate. And there we have relatively few models, I would argue, and a need to go back to theory and get some direction from there. And that's very much what this meeting is all about. Do we have other questions?
Yeah, just
yes, one
follow
here.
on your comments on the data cube. As Professor Guo mentioned, Australia has the government-funded platform called Digital Earth Australia. So I think probably very soon individual countries may have their own, database, the Digital Earth, say China, and so on. So I have a small question to Professor Guo. So is the Digital Earth Society planning to provide some kind of guidance or standards to unify the individual countries' platform? So something like to reduce people can use to share the data, to share the the resources, reduce the uncertainty, like Professor Chen mentioned, and control the quality. Professor Guo.
It's just because in our institute, the Institute of Remote Sensing and Digital Earth, we have right now has 5 satellite receiving stations. So since 1984, we began to collect this data. So right now we have a lot of the data. So among them we have the mid resolution and low resolution the data. Already we have some data sharing program. So open access for that data. Wherefore next step, for the developing countries, what we did, what we do in the future, we just develop some kind of how to say, water receiving station. Water receiving station, that means just using internet technology. You don't need to, take a lot of money to buy some very expensive, receiving station. You just using the internet and just using very, very little money, you can get some your receiving station. Like the 10,000 Chinese yuan, you can buy one. So in the past 3 or 4 years already, we devote this the receiving station, to about more than 10 countries, so they can get this data freely. So I think the one of them, the result, it's a very very good, channel for us to let the developing countries share this. Okay.
Thank you. Do we have any other questions? Ming.
So one of my questions, the GIS database is very poor to handle the temporal information because we didn't put the time in the framework of a GIS database. So there's a lot of a spatial temporal model like diffusions, trajectory. It's difficult to analyze in using the current GIS database. Do you think we need to design a new database for handling the spatial temporal data, or do you have any suggestion to conquer this problem in GIS?
I think I would like to share some of my experience to address Ming's questions. So could be some maybe just some insights. So what we so we have the snapshot, we have the event-based model, and we have, for example, the object-based. So all those spatial temporal data models have been studied in the literature of GIS science. So we have been developing different types of models that are based on those space-time data. But a lot of times we don't have, for example, those theories or formalize those spatial temporal data into those models that we can use those spatial temporal data like what we are using, for example, the object-based or field-based the vector type data set formats or raster data formats. So I think what we have been using the 2 approaches. One is we use our own approach. So we, for example, if we wrote our own code, so we developed our own spatial temporal data model to represent this space-time dynamics. For example, back to 10 years ago, when I was working on my dissertation, so I developed a intelligent agents-based ERC migration model in Yellowstone. So what I did is to wrote my own implementation for this spatial temporal data model, snapshot, object-based, and also event-based. Snapshot, we have the biomass, we have the snow that updated each day. And also object-based, what I used is to represent the movement trajectories of ERC. So we have to combine these different data, spatial temporal data types into the same model. So that is very challenging because you have to have a good understanding about the space-time data structure and also the theories related to these models, and they implement it. So, but for the current, usually, we do the research step by step. So we already have those nice spatial data models. So if we can leverage on those, chime in those temporal components, and then we can, I think, could be a alternative to handle the complexity associated with these spatial temporal data, let's say, data model studies. So I'm not sure that, just some of my personal experience. Yeah.
I think Ming, your question really hits it on the head. This is one of the things we really need to address over the next couple of days. I think the only thing that comes close is the Thorsten Hagestrand's theory, which now goes back many, many years, but has been advanced in the interim. We have another question over here.
So it seems that going forward, more and more emphasis in spatial temporal computing and time and skill is needed in sort of the computer architecture, computer engineering side. Load balancing, setting up clusters, and those things like that. And less emphasis is being put on the actual domain science and understanding of what it is we're trying to load balance. So in your opinion, what do you think the role going forward of domain science in spatial temporal computing is? Should we just be focusing on the computer engineering side? Should we try to be doing both of the domain sciences? How are spatial temporal computing and us here today different than computer engineers that just use spatial temporal data?
That's a great question. Anybody on the panel care to take that one?
Yes, do you want to start?
Yeah. Okay, I can try. I think this is a very challenging question, I would say. I think it was very difficult. I don't think there is, I think, immediately answer or certain answers. Actually, just a couple of days ago, I was discussing with several of colleagues about the big geospatial data. And one, I think the colleague actually working on the computing science side, and basically said, the GIS probably will be die pretty soon. His reasons is feel like, right now, the spatial data actually is not spatial anymore, because every field has been connecting the spatial data, not just geography, right? And they are using the spatial data in even traditionally, which we don't see the many of spatial data. For example, the finance, right, the health, and with the GPS, they're so common, and Google Earth, and I think we have the data. Pretty much every field, they're spatial. They're not, traditionally what we call non-spatial data, currently probably very rare. Every data we connected touched with location, right? So if you look at the technology development, and every big company, like the big, the technology giant, the company, are using the spatial temporal data, not just our GIS, the people anymore. We don't have the privileges to own the spatial data anymore. And they are using, if you look at the world of the Microsoft, the Google Earth, and the world of these kind of autopilot, the companies, they are working on the spatial data. And they are getting into world of the, what do we call spatial data analysis. They are probably doing better than us. For example, if you look at AI field, they are doing the data mining and they are doing the object recognition. They are doing much better job than us. And one of the colleague basically said, I hired an engineer, and he doesn't know anything about the GIS, not anything about the remote sensing. And I basically just gave them the data, and then he's run it and used the algorithm and developed it within a couple of weeks. And they are performing, for example, the object recognition much better than our the software, image processing software. and what's the risk? I mean, make me panic to thinking about, how we as the GIS, what we call our specialist, and to think about, okay, well, actually we should have advantage. Well, actually, I don't think so in some way. And I don't know, I mean, what, in this workshop, can we think about, what's the advantage we have on spatial data computing and on spatial data mining and on spatial data, whatever, let's say, for example, compare with the Google engine and compare with, all of this right now, the artificial intelligence, they're being developed outside of the GS field. I don't know, I think we'll have probably more questions than answers, I think.
Thank you. I call this the problem of persistence, and that is that when you have an enormous database and only a very small portion of it is changing, of course the changing parts are by far the most important, but how do you isolate them and make sure that the computing is devoted to them and not to the vast number of pixels that are remaining unchanged? You want to comment too?
I'd just like a quick comment on that. I think this is a problem that's bigger than the geographic information science community. I believe that there is in my experience, there's sort of a language and capabilities barrier between certain domains and the computer science. Sort of a language barrier there as well. In fact, in biology, I think that barrier rose to such a level that the National Science Foundation also funded the National Institute for the Mathematical and Biological Synthesis. It's in NIMBIOS at the University of Tennessee, just to get mathematicians talking to biologists because of criticism they were receiving that biologists are not mathematically engaged, we'll say. I can't comment, I'm not a biologist, but I see the same thing in the domains that we operate in. I see that there are domain scientists in sociology and even psychology, particularly those social sciences, who have their ways of doing things. They don't speak the language of computer science, and computer scientists and mathematicians, I'll take some blame here, don't speak that language either. So they sort of turn to the way they've been doing things. The thing that I think is dangerous is sort of the hubris that computer science and physics and mathematics can have, because whether we can actually take the data that we're given by these domains, and they will run through our algorithms, we will produce answers, and sometimes those answers are very foolish answers. They're answers that have already been known by the domain. They're answers that didn't consider all of the facts or the assumptions. There was none of that sort of rigorous traditional science that was applied. So I would say it's a very good question, a very good point, and something we should be cognizant of as we move forward with our own careers. I've been guilty of looking stupid as well. Well, maybe I'm the only one. But I think we should be very careful when we begin operating in other domains.
Thank you. Yes, please, just try and keep it to a few seconds.
Your question is my thinking right now. Why? Because, I'm in charge of kind of the bigger data project. So a lot of people involved in this project, people from the, institutions, people from the software institutions, people from geography or geology institutions. But I found that different people have different language. I'm geology language, ocean language, computer language, physical language. So that's wrong. So we should pay attention to interdisciplinary study, cross study. So right now we set up some kind of the group. So give them a top desire. So people should learn each other. People should do some deep, study to make cross this way. So we should in the future have the, one common language. That's very, very important.
So thank you for that comment. With that, I sort of have to close the session.
Yeah, before we close that, in fact, I want to ask a question to all our panelists. If you have the power to solve one problem in big geospatial data, what is the one? You don't have to explain, just state the problem that you want to solve.
There goes the coffee break.
Are you from the national lab? You should give an answer.
We want to hear from all of you, please.
I think I would solve the problem that that I see growing. It has nothing to do with databases or anything else. I think it's the question of why are we doing this? What are the questions that we are wanting to answer before we run off and start grinding algorithms and producing displays and charts and stuff? I struggle against that as well. I'm very enthusiastic to begin running numbers.
Thank you.
Well, me too. The first one, the data standard, and the second one, who will use this data. You know, that's a really fun problem.
There are so many questions. I think I could like the geospatial data could help, but I think one if I have to just say one, I will probably asking about more on the disease, like the tracking the disease. I think because we have large population. How we're going to track them, and then how the tracking the movement and then spreadings. I think.
I think I would be more interested in solving space-time complexity-related problems. So that can be informed by the advancement of big data and also cyber infrastructure. So originally we can only think about it, but now with the availability of these HPC resources, cloud computing resources, really want to move from the theoretical discussion down to the modeling level, and then really use those computing skills to tackle the space-time complexity-related problems. So maybe a little bit generic, but that's what I have been working on. Yeah.
And I'm the chair, so I get the last word. I think we have some good theories of space. I think we have some good theories of time, but I don't think we had good theories of space-time. So if anything, perhaps the valuable contributions for the next 10 years are going to come from philosophy or physics. I'm not sure where, but I'd like to see them come out of this community. So let me just say what we're about to do. We're going to take a brief coffee break. When we reconvene, we will be in 3 breakout sessions. Sessions A1, A2, A3. Session A1 will be in room S020. We're currently in S010, so the same floor. That'll be on modeling. We have session A2 is on computing optimization. That'll be in room S030. And session A3 will be on health applications in S050. So
yes.
with that,
well, thank you, Keith. Since we're all here, we want to arrange the group photo now instead of waiting after everyone break out. So when are we going to have it?
It's the staircase coming. Yeah. Sorry, we have a small modification on the program. So while we're all here, and thank you for the panelists. I don't want to hold you on the stage. We will gather before we break for the coffee. Please find a spot on the staircase when you come down into this floor, right? We'll take a group photo quickly, and then we'll have the coffee break, and then move on to the breakout sessions. So photo first, coffee break second, breakout session.
That's a challenge. I've never seen a group photo done quickly.